Right, open loop response to a frequency signal input is used to deduce the closed loop response time. This is an open loop system, i.e. it doesn't have a feedback loop, right? This is just feeding a frequency into a system that's represented as GH, and we're measuring the output from that system. So XT is our input, YT is our output. XT is a sinusoid with an amplitude X and a frequency omega. And our output, we'd expect some sinusoidal output as well, assuming the system is in steady state. And that output is going to have an amplitude Y, and it's going to have the same frequency, but it could have a phase shift of phi, phase lag. So we could actually compare the two signals, basically just tapping the signal on the input here, and then also tapping the signal on the output, plotting these against each other. So we have the input blue signal and we have the output red signal. Right? So we can see that the magnitude of the output is less than the magnitude of the input. So the system is doing something to reduce the amplitude of the output compared to the input, but it's also doing something to cause a phase lag. So it might be like about a 45-degree or up to 90-degree phase lag between our input here and our output here. You're seeing that phase lag there right through. So we have this sort of setup. The nice thing about frequency response is it's possible to do something called system identification. And that's where you literally take a system and you put a sinusoidal input onto the system and you measure the output, and you can plot them just like I've plotted them here. And by comparing those mathematically, you can actually deduce the transfer function of the system. So that's called system identification. So we can determine frequency response either experimentally, like I just described, or you can calculate what that's going to be from the transfer function. So most of what we're going to do now is going to be calculating our outputs, the signal, the output from the system based on that input, which is going to be, and the relationship between the two is determined by that transfer function. So as we go through using this frequency approach, then we're taking a second order approximation of the system. For higher order systems, we can assume that the second order equivalent is valid. So we can describe the system in terms of its damping ratio and natural frequency, as we have been doing for our second order systems up to this point in time. Now, when we're dealing with a frequency response, we have new figures of merit, or let's say proxies for the performance of the system. And those are these ones listed here: gain margin, phase margin, and maximum magnitude, right? And the two more important ones are the gain and phase margins of those three. And we also have a range of different ways of displaying our frequency response data. The one we're going to deal with in the course is this Bode plot, right? I keep doing this line, I don't know what's happening there. Right, we're going to do the Bode plot, but we'll have a quick look at the Nyquist and the Nichols. We won't go into them. Looking at this, not considering, except for a quick little look, and we're not considering this one at all. Now, to proceed with frequency response, we have to understand the different forms in which we can represent the relationship between these lines, our red line here and our blue line. How can we represent the relationship between these? Well, we can do it in a number of ways, a couple of different ways. We can represent it vectorially, right? So if I represent this vectorially, I have got my input vector here, Now it just looks like a line, but actually this is a frequency, right? So it's at an angle of 0, and it's a magnitude of xi, right? Right, so we have our x in and our x out, and then you can see it has also this phase, which is then becomes the argument or the angle between these two vectors. Right, so this is a vectorial way of representing our frequency response, and our gain is our output magnitude x out over our input xi. Right, so it's the relationship between those, just the quotient of those two, and then our phase is the angle between them. So that's a vectorial relationship. So what we can actually do is we can transform our transfer function from the S domain to represent it in as a frequency by substituting S for j omega, sorry. Then we can also express a frequency transfer function in terms of a magnitude and right, then we can also represent it as, and this is a sort of vectorial, and then we can also represent it by separating our phase from our magnitude. But now our magnitude, instead of just taking a raw number of magnitude, we're actually taking a decibel, right? And why would we do that? Because what that does is it allows a very large range of different magnitudes to be represented on the same scale without it being ridiculously exponential, and so it allows linearization of nonlinear relationships basically by using this decibel scale. We're already familiar with decibel scales because we have done them a bit in instrumentation when we're dealing with gains and amplifiers and so on. This is exactly the same thing, because really a controller or a compensator is a type of amplifier of an input of some description. All right, okay, I've forgotten how these labeled. Let me get rid of the excess. And so we've got the transfer function form, frequency response form, polar form, and then we've got the magnitude and phase form. So let's look at how we represent these frequencies using Bode plots. And with Bode plots, you have two separate plots, a gain plot and a phase plot. So we plot each one versus the frequency. All right, so as frequency increases in our system, we start with close to 0, and you got to sort of infinite radians per second, right? And as you do that, the relationship, the gain relationship changes, so the magnitude, and also the phase changes, this phase shift. Just going to step back again to our first slide and think about what that means practically. If we're changing our input here, right, well, how are we changing it? We're really changing the frequency of our input. If you think about a very slow or low frequency input, something let's say close to 0, let's say it's like 1 radian per second or something, right? So that's a very slow, sub 1 hertz. Well, yeah, it's 3.14 radians per full revolution, right? So you're kind of rotating at maybe 1/3 of a cycle per second. Very, very slow, low frequency oscillation. That means that the system would generally, have time to keep up with what's happening on our input. So as this oscillates, then the system could establish steady state, and it would follow, it tend to be able to follow the input on the output side, because the frequency is low. So we might find that also, you get probably a closer to like a 1-to-1 relationship between the magnitude of the input and the output, between x and y. Or if not, then at least it's, as low frequencies you're able to maybe even have a higher, if it's got a gain, some gain inside this transfer function here, you might even have a higher magnitude output. Now, if you go up to very, very high frequencies, on the other hand, so you're now increasing our input frequency, keep increasing it, keep increasing it, keep increasing it, all the way up to a very high frequency, that's like a million radians per second. What's likely to happen is, if this is a physical plant and it's got physical dynamics in it, let's say it's got mechanical elements with masses, right? The likelihood is that the time constant of this system has been well exceeded by the frequency of the input. So basically, you're oscillating this input at a very high frequency. The system wouldn't be able to cope. So as you're accelerating it up, the system will be lagging, because now the mass has to start to accelerate based on, say, the change in force on the input. But by the time it starts to accelerate, you see at this point now, the input is coming down. So now you're going to be decelerating this, and so on. So you've got a phase lag, but now what's happening more and more is this, as the frequency increases, this thing's going to kind of level out, because it's not going to be able to follow the very high frequency oscillation of the input. So with the Bode plots, what we're doing is we're plotting the magnitude and phase, the magnitude in decibels and phase and angles, as that angular frequency changes. Right? So here at low frequencies, this is 0.1 of a radian per second. Right? You're seeing you have a magnitude of like 30 decibels. So in other words, the outputs magnitude is higher than the input. Right? So you get actually amplification here. Right? And it comes down to the point where we have zero gain. So there's zero magnitude gain. That means our output and our input are the same. Right? But that happens at a slightly higher frequency. So as our frequency is increasing, what's happening is that the magnitude of our system, the output over the input, is starting to drop off. And then when it goes above a certain sort of critical value here, it goes into a negative territory of our magnitude plot. You see down here is negative numbers. As the frequency is increasing, the output is going to end up being smaller than the input. Right? This is as the frequency is increasing. It's just what I was explaining before on this slide. Basically the ability of the system to follow is being compromised. So now you basically have less and less amplitude on the output side of it, because this input is oscillating too fast for it to be able to follow. What about the phase? Well, the phase also varies with frequency. So the phase lag, in this case, at a low frequency, we have about a close to 90 degrees phase lead, actually. Well, let's say about 70 degrees. As you're increasing, you get to a point around here, in this case, where the phase is equal. So there's zero phase lag. So in other words, the systems are, input and output are harmonized. But as you continue to increase the frequency, then you can see there's a negative phase lag here, as you get up to higher values. Right? And this one sort of levels off towards around minus 180 degrees. Right? So that's the relationship between the input and the output. And it's expressed in the Bode plot in terms of two plots, magnitude and phase. And we're going to talk about those quite a bit. How do we plot it by hand? Well, by hand we use this paper, and you'll be provided with this paper. You can get it on my e-learning to print for you to do your exercises, tutorials, and so on. Well, what you basically have to do is draw the axis, which is log omega, right? And you have to determine what each of these. This is semi-log paper, right? So it's linear, going up and down here. Oops. All right. So on this side we plot our magnitude, in decibels, and we center it at 0 decibels. On the other side, we plot our phase. Whereas in MATLAB, as you saw on the previous slide, you have two separate plots, magnitude and phase. For various reasons, when we're doing it by hand, we do it as one plot, and we plot both the magnitude and phase on the same plot. But we make sure that we align minus 180 degrees phase with 0 degrees decibel. So you could then mark off your scale. You might say, okay, this is 10, 20 dBs, 30 dBs. So just have a linear scale for your decibels on the right side, and then you have something similar on the left side. You're starting at minus 80, so this is minus 170, minus 160. Then if you want to mark in between, you notice that these are not evenly spaced out because, of course, it's log linear paper, so you can't necessarily put all of these markers in. You don't need to. I normally just put the 10s in, right? But you just have to be careful to make sure you're measuring correctly to get these other ones in between these interim markers, right? This is 0.5, this is 0.4, 0.6, 7, 8, 9, 10, right? So how to plot semi-log graph paper. That's our Bode plot format. Next, let me just introduce you to Nyquist and inverse Nyquist, just to broaden your knowledge. You won't be required to actually plot these, but you should know about them. So Nyquist uses this polar form, or the vectorial form of our complex number. Remember, GS is a complex number, and S, G, J, omega is a complex number as well, but now we've substituted our S for our frequency, and we're going to sort of prove in a bit that we can do that, right? And then we can express our frequency domain complex number as in this polar form with a magnitude and an angle or an argument or a phase. So that's what we have here. Now, how do we plot it? Well, we you look for a complex number for each frequency value, right? So we're going to change omega, and for each value of omega, we'll get a value for r and phi. We get a value for the magnitude and the angle, or the arguments of that particular location. So at low frequencies, we would start out, you know, if omega is 0, we'd end up being on the negative. All right, so sorry to should have said this is now also plotted on an Argand diagram, imaginary and real, because what we're doing is we're plotting the location of a complex number, and then we're going to change that complex number as the frequency changes. So for each value, we calculate our r, and we calculate our angle phi. Right, so this is r1, phi 1. Then we're going to go to our next point, and we're going to calculate r2, phi 2. Then we're going to our next point. So this might be omega. Let's say this is omega equals 0.5, omega equals 1, omega equals 2, omega equals 10, omega equals 100. We're just hypothesizing, right? So at omega equals 1, we calculate what's our magnitude, r3. That's the length of our vector on the Argand diagram. And we calculate what's the angle, phi 3. That's the angle from the negative imaginary axis for us to plot our response. Right, so we continue like this. until you've plotted a number of points, and then you could join the dots, literally join the dots, as I've shown here in this blue line drawing over in black, and you end up with a kind of line on your S-plane, on your Argand diagram, that represents how this system changes with changing input frequency. Right, now there are some key points along here, like for instance right here you can see, no, didn't want to do that. Right here you can see that the our plot crosses has 0, our imaginary component is 0 at this point in time. Right, so there are key values here, and you can see as well that the plot comes in towards the origin. As the frequency increases, the magnitude reduces and reduces, the R, as the frequency is increasing. So some of these things are important in terms of the characteristics of the system, but this is just so you get an idea of how a Nyquist is plotted. Sometimes you do what's called an inverse Nyquist, and then to do that you plot the inverse transfer function. So now when you have a small omega, you're starting in the origin, and the plot will work out. So again, each of these is a value of omega. Now we start with 0, small values of omega, and we build up. All right, but again, for each inverse, for the inverse transfer function, for each value of omega, you'd calculate your R, and you'd calculate your phi. Right, so that's all I'm going to say about this Nyquist and inverse Nyquist. You can use it to plot the behavior of the system. Let's look at a couple of advantages and disadvantages comparing our root locus with our frequency methods. The root locus, with which you're quite familiar by now, has some good advantages. It's a good indicator, for instance, of our transient response. You know, you can get a specific closed loop root location on the root locus, and you know for that specific closed loop root, what's the damping ratio going to be, or the approximate damping ratio for a second order system. What's the natural damped natural frequency? Therefore, what kind of response characteristics are we going to have to our system? What's the like all those characteristics of the step response, peak overshoot, rise time, time to peak, settling time, etc. So that's a nice advantage for the root locus, right? So give that one a tick. But it also explicitly shows the location of all the closed loop poles. We like that because you can look at it, you can sketch it quite easily. When you get used to it, it might seem a bit intimidating initially, but when you get used to it, you can actually pretty easily, based on the transfer function, determine where the closed loop poles, where the poles and zeros are. You could plot your locus, or at least sketch it, get some key points in your locus, determine therefore where your closed loop poles or closed loop roots are going to be. And then you can see pretty easily trade-offs in the design as you add, as you add poles and zeros, as you change the design of the controller, you could figure out what the locus is doing and how that's going to affect the behavior of the system. So those are some good advantages on the root locus side. On the frequency method side, it does complement our root locus techniques. So it's kind of an additional tool which we use when we're doing our design. You can infer both performance and stability from the same plot. So if we just do our Bode plot, then from that Bode plot we can see whether we're stable immediately, and then we could also get a sense of how stable we are, and through one or two steps we can still determine what our time response is going to be, like we do with the root locus plot. And this is an important one here. We can in fact measure data to get this, as opposed to having to go from a transfer function model. The fact you can do this thing called system identification. That's very important with frequency methods. You literally actually take the system, put a frequency on it, measure the output, and then compare the input and the output to get your Bode plot and your Nyquist or whatever you want to use. Right, the design process can be independent from the order of the system. So higher order systems are sort of easier to handle, and that's, I think, an important part. So like complex systems where you don't necessarily have a good data transfer function model, you could get the behavior through identification. And higher order systems can be handled much more efficiently and effectively with Bode plots. Time delays are also handled quite well. And then the graphical techniques, they're relatively simple, not overly simple, but relatively simple. Right, so what about disadvantages? Disadvantages on the root locus side, you have to have the transfer function. So you have to create your model to be able to plot the root locus. Sometimes difficult to infer some performance metrics, like you don't know necessarily how much you have in hand before your system becomes unstable or something like that. Right, so that could be a bit of an issue. Like you can't just look at a root locus and say, okay, I can get a sense quickly of how much additional gain I could add before the system becomes unstable. You don't know by looking. It's hard to determine the response to steady state sinusoidal inputs. So it's good for step inputs, where you're going from set point A to set point B. But some systems do have frequency inputs, so it's not so easy to determine the behavior of a system using a root locus based on sinusoidal or oscillating inputs. And like I said, it's hard to infer these stability margins, which is what we're very interested in with the frequency response. Frequency response disadvantages, it can be a little harder conceptually because you have to think in terms of the frequency and the oscillation of the system, and how do you link that back to step response, time response, for instance. And a kind of biggish disadvantage, especially when you're doing it by hand, is this. It takes a while, right? Plotting by hand takes longer and is more complex. You'll find that out as you have to go through and do this and also do it in your exam. So you have to make sure you give yourself some good time for the Bode plot question in the exam, because you're going to have to go through, crunch the numbers, and plot it. Okay. If we have well, let me just, let me press on. If we have a transfer function, this is GS, we can, G as a function of S, our S form transfer function, we can compute the frequency response by substituting J omega for S. And then we evaluate the resulting complex number. So we're going to use the same mass spring damper system that we used before when we did the derived, mathematical modeling. We derived the equation of this mass spring damper, and so I don't need to go through that derivation again. It's fairly straightforward. The main change now is I'm going to take the differential equation, but I'm going to put an input xi, so our xi here, instead of just being a step or a position or a constant value, that is going to actually be sinusoidal. So now we are oscillating our system back and forth with a certain amplitude xi and with a certain frequency omega, right? So this is now the input function for our system, xi sine omega t. Our transfer function, or let's say our differential equation describing the system dynamics, all I've done here is I've equated that to our input forcing function, xi sine omega t. Right, so all the rest of this is familiar to us, right? Because we derived that last time. If the sinusoidal input is applied, then say the system starts from rest, and I activate a sinusoidal input. Right, so now I'm oscillating, I'm forcing the system with a sinusoidal input. It was at rest before. It's going to have a transient part. It's going to start to accelerate until the system comes into a steady state condition. Right, so we're going to have a transient component, but we're also going to have, and this is the part we're interested in, it should settle in to a steady state sinusoidal oscillation. And when it's settled into that oscillation, the frequency of the mass or the output is going to be the same as the frequency of the input, omega. Right, so our output frequency is going to settle to omega as well. Now, for the purposes of frequency response, we're not interested in the transient. We're only interested in the steady state motion. So we're going to write our input in the complex form. We said before xi of t equals xi sine omega t, but now we're expressing it in our exponential form, xi e to j omega t. And our output is now going to be expressed as x out or xo e j omega t. So now we have our input and our output, and I'm substituting those back into all the places where we've got x out here and our x in here as well. Right? So I'm putting all those terms into substituting them all for all the input terms for this, all the output terms for this. So here's one of the output terms, each output term here. We're expressing it this way now. X double dot, XO double dot, is going to be d2 by dx squared of our output, which is xo e j omega t, right? And that second derivative, well, let me start by just doing a single dot derivative first. X out dot equals d by dx, x out e, j omega t, and that is going to be j omega times x out e j omega t, right? So then if we do a second derivative, then we're going to have j omega squared x out e j omega t, right? So that's why we have for our x out double dots here, bring that down here, you've got your j omega squared x out e j omega t. So that's property of what happens when you differentiate an exponential term. You multiply the resultant by the power, the differential power. So we've done that twice. So we've got a j omega squared times the mass. The mass is a constant, right? This one we've done it once. So we've got j omega x out j omega t. This one just doesn't have any differentiation, so that's a pretty simple substitution, as is this one. Right, so That's what we've done here. Now, okay, let me move on to my next slide. So this is the expression we have when we substituted in our term for the input and the output. And of course, we want to rearrange it into transfer function form. So we're gathering all our x outs together on one side. We're dividing both sides by xi, actually. Dividing both sides by, the factorized elements here. The nice thing is all these terms, the e, j, omega t's, these all cancel out, right? So they're gone. And we end up with a function, a transfer function that looks really similar to the one we got when we did the other approach using the in taking Laplace transforms and doing that way. In fact, this is the function we got when we did Laplace transforms. And you can see we could have actually just taken that Laplace form function and replaced all our s's with j omegas. So if we just taken our s and put j omega into here, j omega into here, j omega into here, then we'd have gotten the same function. Right, so the point of this little exercise with our mass spin damper is we could have just substituted s equals j omega, and this is something we're going to use right through now with our frequency domain analysis. Whenever we have a Laplace transform function, we can substitute all the s's for j omegas, and we just make it into a frequency domain transfer function. Right? And this is now talking. This is in the steady state frequency response, which is what we're interested in. So we're going to look at a couple of examples. The first one is a simple first order lag, right? 1 over 1 plus s tau. And this could be a servo motor or temperature control, very simple. Now, before we do our substitution, let's just remind ourselves about some complex number basics, because we're going to have to do some complex algebra here. So if this is our complex number z, what is the modulus of z? The modulus of z, now remember, basically what we're doing here is we're dividing two complex numbers. So generically, on an Argand diagram, you've got an imaginary and real, and you've got, let's say, point A, let's call it alpha actually, and then we're going to have here point beta, and alpha is at coordinates A comma B, right? So it's going to equal A plus JB. Beta is at C comma D, so it's going to equal C plus JD. Right? So what we're doing is we're dividing one by the other, so to get the quotient. And when we mathematically to get the modulus of this quotient, then it's very simple. We just take the modulus of alpha and divide it by the modulus of beta. So that bit's pretty straightforward. What about the argument of z, the resultant of this quotient? Well, that one's a little more tricky, but not too much more. The inverse tangent of the denominator, right? And then you have to subtract the inverse tangent of, sorry, the numerator minus the denominator. Okay? So let's now apply it to our first order lag. Well, the first thing we're going to do is substitute j omega for our s. So now our transfer function looks like this, our frequency domain transfer function. We've got our j omega in there, and of course that's a complex number. You can see it's clearly enough that it's a complex number. And if we're expressing a complex number, we can express it in different ways. We can express it in terms of x and y in this case. We can express it in polar form. We can express it in as an exponential term. But in this case, we're going to use our polar form. So we're going to get a magnitude and we're going to get a phase for this particular complex number. So what's the magnitude of this complex number here? Well, based on what we just did, the magnitude is the magnitude of the numerator and the magnitude of the denominator. Magnitude of the numerator is 1. The magnitude of the denominator is the square root of 1 plus omega squared tau squared. Right? That's our magnitude R. What about our argument or our phase? Our phase is going to be our argument, which is inverse tan of the imaginary part of the numerator, denominator, the numerator over the real part of the numerator, minus the argument of the denominator, which is the imaginary part of the denominator over the real part of the denominator. There's no complex part on the numerator, so that means we're going to have 0 for the imaginary. So this is just going to go to 0. And we end up with this part minus tan to the minus 1 of our imaginary, which is omega tau over 1. Now, we're going to look at a special case for this first order system, and we're going to look at the case where omega is 1 upon tau. So if omega is 1 upon tau, then we're going to have 1 upon tau squared here, and we're going to have 1 upon tau here. So these taus are going to cancel, so it's going to be 1 inverse tan to the minus 1 of 1. And this one is going to be 1 plus 1 square rooted, so it's root 2, right? So in these special cases, the magnitude is 1 upon root 2, which is minus 3 decibels. And the angle is going to be minus 45 degrees. So let's plot these. This is a Bode plot, a sketch of a Bode plot. So this one is our gain, M, right? And we're just identifying one point here, basically. And we're saying at this point, omega equals 1 upon tau. What's this going to be? This is going to be minus 3. Gain in decibels. And we're also saying that at this frequency, omega equals 1 upon tau. For a first order lag, just a very simple little system we have here. At this particular condition, omega equals 1 upon tau, then our phase is going to be minus 45 degrees, right? As per identified here. If omega is much less than 1, in other words, omega is approaching 0, let's say, right? That will cancel this. And so R is going to be 1 upon 1. And so 20 log of 1, the magnitude is going to be 0. Right? It's going to approach 0. Because if you take the log of 1, you get 0. So let's not say it's equal to 0, it's approaching 0, because we're saying omega is much less than 1. So as omega gets smaller, in other words, and down towards 0, then our magnitude approaches 0. And if we say if omega is, let's say, much bigger than 1, then basically this 1 is going to disappear in comparison, especially since you've got an omega squared here. So you're going to end up with R equals 1 upon, now the tau is also going to probably become irrelevant as omega gets larger, because that tau term, probably be small comparison. So you're going to end up with 1 upon omega, because it'll be square root of omega squared. And so you can do similar tricks as well with the phase and say, okay, what happens if omega is much smaller than 1? Then this is going to go to 0. So for the phase, I've run out of space here, but if I write it here, if omega is much less than 1, then what's happening to our phase? Our phase is going towards 0. So you see it's coming towards 0 here, right? At low values. If omega is going towards, let's say, infinity, then our phase is going towards what? If omega is going to infinity, then it's inverse tan to the minus 1 of infinity. This is where the property of the tangent comes in a very interesting way, because of course our tangent, if we take the inverse tangent, well, or if we take the tangent of 90 degrees, it gives us infinity. If we take the inverse tangent of infinity, it's going to give us 90 degrees. Right? So in this case, it will be minus tan to the minus 1 of infinity. So in other words, minus 90 degrees. You can see that as omega goes to infinity, then our phase is going to minus 90. So we can do these kind of things, and I'm just showing you in a very simple first order type system, but we can do the same thing as we break down any system we have into component parts and apply the same kind of approach. So let's look at the frequency response for a prototype second order type system. This one gets a bit more interesting, but we're going to use the same method that we did before. And all our S's, we're just going to drop in what? Our J omega, right? So we're dropping in J omega every time we see an S. Right? That will transform our function from being an S domain to being a frequency response or frequency domain transfer function. So let's do it. Substitute S equals J omega means our transfer function X out over X in is now a function of J omega. We've got a J omega squared, then we've got our 2 zeta omega n J omega, and then our constants omega n squared. Right? Now this one, J omega times J omega equals J squared omega squared. J squared is minus 1. So that means this is minus omega squared, right? So we now have a constant which is omega n squared, or a real term, let's say, which is omega n squared, and we also have another real term from this squared complex, which is minus omega. So we put them together now on this side here. So here we have a real term on our denominator, and we have this is our imaginary term, and then we just have a real term with no imaginary on the numerator. So what's our gain? Our gain, just in the same way as we calculated it for the first order system, on our real on the numerator remains omega n squared, but on the denominator it's our real part squared and our imaginary part squared. And in terms of our phase is going to be, well, there's no imaginary part on our numerator, so again, it's basically 0, which is 10 to the minus 1 of our imaginary numerator over our real numerator minus this, right? Really speaking, right? But this goes to 0. So you just end up with a negative 10 to the minus 1 of the denominator imaginary part over the denominator real part. But what we're going to do is just to, well, not simplify exactly, but to, because it makes it useful to do, we're going to divide throughout by omega n squared. So if I just skip back up, this expression here for gain, we're dividing throughout by omega n. So our omega n will come out here, and we are dividing here each term by our omega n squared. Because remember, this term is squared here, so we are eliminating it here. We can see now this goes to 1, this goes to 1, and this is omega upon omega n squared. So that's what we should be looking for on our next slide. Right, yep, our 1 here, our 1 here, omega over omega n squared, and, well, the real part, well, we divided by omega n squared, so that's why you end up with omega over omega n here, right? So the peak value will occur now. You can see the peak magnitude. You see there'll be a peak value of magnitude. It's going to be at its highest possible value when this negative is at its lowest possible value, right? So when the denominator is at its minimum, that's where you're going to get your peak value. That would tend to be where, you know, you've got a minimum value where omega equals omega n, because this one will go to 1, this one will go to 1, you're going to have 1 minus 1, so this whole term cancels out, so you just end up with 1 upon root 2 zeta for the magnitude. In terms of the phase, then when we've normalized, you can see the imaginary part is on the of the denominator divided by the real part of the denominator looks like this. So again, we can get some useful sort of locators on our curves, on our phase curve, because you can say when omega equals 0, then this whole thing is going to go to 0, and our phase lag is going to be 0. So as omega approaches 0, that means that our phase is going to be approaching 0. And when omega equals omega n, this will go to 1, this will go to 1. So we're going to get the inverse tan. How did that work out? When omega equals omega n, then right, we've got to, that's right, we've got to, these will cancel each other out. This goes to 1, 1 minus 1 is 0, right? So we're going to, when omega equals omega n, this is going to 0, so this becomes infinity, right? So we've got tan to the minus 1 of infinity again, which gives us our minus 90 degrees. And then, well, as omega goes to infinity, then this will go to infinity. This will go to a very large number as well. And basically, you're going to kind of max out at phi equals minus 180 degrees. Right. One last identity is that our resonant natural frequency is going to be equal to our undamped natural frequency times root 1 minus 2 zeta squared. So basically what this is saying is that there's something called a resonant frequency which exists, and it's slightly offset from our natural frequency, and the offset depends on the damping ratio. So if we have a very low damping ratio, our resonant natural frequency will be the same as our natural frequency. If our damping ratio increases, say to, let's say, about close to 1, to about 0.8 or something, then what's going to happen is you're going to have a bit of an offset of the damping ratio, right, of the natural frequency. Not a very large effect, but it's something you have to bear it in mind and note that. So these curves, these are sort of, to wrap up with, analogous to our second order system response. Right, remember that was the second order system response to a step input. Now this is the second order systems data for frequency response. So again, this is our Bode plot. This is our magnitude in decibels. It starts out at 0. I think we said that on the previous slide. Right, the peak will occur when the denominator is at a minimum around natural frequency. If we have a very small value of omega, this will go to 1, and this will go to 0, so it's 1. The magnitude will be 1. If you take the magnitude of 1, so it's saying if omega is approaching to 0, that implies the magnitude is going to be 0 dBs, because if we take log of 1, that gives us 0. So sure enough, for low frequencies, we get close to 0 dBs. Then we see if we have a low damping ratio, like 0.1 here, then we see a peak, a resonant peak in the magnitude. This is resonance. And you see that at a low damping ratio, it's sort of slightly offset. As the damping ratio increases, this resonance moves slightly. Right? The resonant frequency isn't completely the same at all damping ratios. And that is because the resonant frequency is a function of the damping ratio, as we saw on this previous slide. Alright, so you can see this is standard second order systems data for varying damping ratios for our natural frequency response. We also see here for all damping ratios, as frequency goes down to a very low value, then our phase goes towards 0. As it goes up to a high value, our phase goes towards minus 180. But in all cases, as our phase goes through omega equals, switch it up here. When our frequency is our natural frequency, we always go through minus 90 degrees phase. Right, so all of this tells us how do we sketch the Bode plot for a second order system. Well, these are the data and these are the points that we need to remember. Once you remember these basic points, it's actually not too hard. Right? Really what you need to calculate is things like, well, what's your natural frequency, so you know where this resonant peak would tend to occur. You know what the if you know what the damping ratio is, natural frequency, you can calculate how high your resonant peak is, and you can calculate what the resonant frequency is. And apart from that, as the frequency goes towards infinity, then there's a certain gradient that this will settle down to. And we know that as omega goes to infinity, that the phase is going to minus 180. As omega is going to 0, the phase is going towards 0 degrees, right? Let's go through how we actually create a Bode plot. Direct calculation of frequency response is a bit tedious. There's a procedure for approximating it. So when I say the frequency response, we're talking, remember, about the elements of, for some transfer function g of s, we transform it to a function that's in terms of j omega, and then a transfer function expressed in frequency terms, where you've got j omega as your operator effectively, that can then be expressed as r theta, and which is magnitude and argument, or the form we tend to use, which is 20 log r, and a separate expression for our phase angle phi. All right, so this is our magnitude, this is our phase, and we plot these plotted versus omega in a Bode plot. An NB Bode plot is semi-log. So you use a logarithmic scale for your omega, and you use a linear scale for your magnitude and your phase. Bearing in mind that magnitude has already been converted into a decibel format, which is a logarithmic format itself. As with the time response, frequency response can be characterized in terms of its natural frequency and its damping ratio. So we can get from certain metrics that we derive from our Bode plot, and those metrics are our margins, our gain margin and our phase margin. We can relate those back to natural frequency and damping ratio. So let's look at how we go through the sketching process for Bode plots. We use special graph paper, as I just mentioned, and that's semi-log or log linear graph paper. So log of omega to the base 10 is plotted against decibel gain on one axis, and on the other axis, when we're plotting by hand, we tend to use the same ordnance and two separate abiscas. Right? On the other axis, we use the angle, the phase angle. So we have to calculate our gain, and we have to calculate our phase. And we're calculating our gain in decibels, and we're doing it by taking the magnitude of our transfer function, and then we're taking 20 log 10 of that magnitude, and that gives us a value for our gain in decibels. We have to know about our frequency scales, and we could either work for frequency in decades, which goes up in factors of 10, or we can use octaves. If we use decades, which we tend to do most commonly, then every increment on our semi-log scale is a factor of 10. So the first increment would be 0.1, the next major increment would be 1, the next major increment would be 10. So these increments, of course, being a log scale, they're evenly distributed. So if we have this as our 0.1 and this is log omega along this axis, then we could distribute our values evenly. Our first value will be 1.0, 10, and 100. So this is if we're using the decades. Right? If we were to use octaves, then it would go like this. Right? So that's how we arrange our scale. Normally, like I said, we use the decades approach. Next thing, we're dealing with the transfer function. And we're taking the transfer function for our system. It's the open loop. This is important. So we find the open loop transfer function of our system, and then we break down the open loop transfer function into different factors. And there are only 4 types of factors that we'll have in our transfer function. We could have a gain, a pure gain, which is a constant. We can have a pure integrator or a pure differentiator. So we're calling that the first, like a pure element, just either an S on the numerator, or for a differentiator, an S on the denominator for an integrator. The next type of element we can have, or the next type of factor, is a first order lead or a first order lag. So this one is a lead. Sorry, this is a lag. If it's on the denominator, it's lag, and this one is a lead. Why is it called lag and lead? That has to do with the phase lag. So if you have a 1 over s plus tau term, a denominator expression, and a 1 on the top, then this is going to introduce a phase lag between the input. Remember, all the time we have our little system, we're dealing with that, and if we have a term like a first order term with a 0, which is 1 plus s tau, this will give you phase lead. So effectively what that does is it shifts the blue line, which is the output line, ahead of the red line. If this transfer function is a lead, it will mean that the output sort of precedes the input phase-wise. And so the whole blue line will shift to the left. So that instead of having a lag here where the output is trailing behind the input, you could actually end up with a lead where the input would be preceding the output. The 4th type of element we could have in our transfer function is a second order lag or a second order lead. So this is familiar to a standard second order transfer function. This is the same function, but it's the quadratic is on the numerator here. So this is a lead, and the first one on top is the lag. So let's have a look at an example, easiest thing to work with. So what are our elements in our transfer function here? Breaking down the transfer function, we definitely have, this is going to be a pure gain. We have a first order lead. It's on the numerator, it's a lead. We have a pure integrator. And we have here first order lag. And we have in the quadratic second order lag. Don't know why the pen keeps doing these strange lines. See? Right, this one's the second order lag. So we have all 4 types in this transfer function. So let me clear off all my scribbles there. We have a pure gain, and we could call that G1 because we give each of our terms a name. Our first order lead on the numerator as G2 with s plus 2. Our pure integrator is our 1 upon s. First order lag is 1 upon s plus 4. This element, of course, and then our final one, of course, is going to be the second order lag. Yes, this one here. Okay, so we have our all four different types of elements, and we've actually got 5 factors in this transfer function when we break it down. So now we can, and this is one of the nice things about the Bode plot approach, is that you can break down your transfer function, and you can then effectively create the plot for each element and then add them back up together. So that's a big benefit of the Bode plot process, is you could get a more straightforward or more simple Bode plot calculation for each element, then you can build it back up by adding them together. So for the gain, we're going to go through each element and look at how it's plotted. That's our term G1 equals 3. That one is straightforward for getting the gain or the magnitude plot, the gain plot. We just take the value k, take the log of it, and then multiply it by 20. So in this case, k equals 3. So we're going to have a contribution from this pure gain element in our, or this pure element gain factor in our transfer function. That's going to give us plus 9.54 decibels, and that's going to be true for all frequencies. So that's a straight line across our frequency curve, as we see here. It's just a straight line right across. It doesn't matter what the frequency is, we're always going to get our gain of 9.54 decibels there. But gain, because it doesn't have an imaginary part, it doesn't make any contribution to phase. So there's zero contribution to phase, and you don't have to take that into account. A pure gain is just giving you a magnitude contribution. All right, so hopefully everyone got that. That's pretty easy. Let's move on to the next element, which is, every element we go to get a little more complex. So this one now has a 1 upon s. Now with this, we do have to take our transformation from the s domain to the frequency domain. And remember last time we showed how that could be done by just substituting j omega for every time you have an s. Right, so in this case, our transfer function will go from being 1 upon s to this 1 upon j omega. All right, so this is our transfer function now. G equals 1 upon j omega, or G3, we could say, in this particular situation. Now, once we have that j omega form, or the frequency domain form of our transfer function, we can apply our normal rules that we looked at last time about how you treat with that. So the magnitude, first of all, of that transfer function is going to be 20 log base 10 of the magnitude r. So we said r equals magnitude j omega equals, it's going to be the magnitude upon 1 upon j omega, right? But we're expressing it as m. And to get m, we're taking 20 log 10 of that r. So the thing is, if you take the magnitude of this, then you're going to end up, if we remember our little basic quotient rule for complex numbers. If we have a generic complex number z, it's a quotient, and the magnitude of z is going to be the magnitude of a squared plus b squared, square root of a squared plus b squared, over the square root of c squared plus d squared. Right? So if g equals j upon 1 upon j omega, then the magnitude of j omega is going to be root of 1 squared over the root of 0 squared, because there's no real part, plus j omega all squared. There's going to be 1 over the j squared becomes minus 1, and so you're taking your minus 1, square rooting it, and you just as becomes 1, and then you just end up with root omega squared. Okay, now that's equals this value r, but we're expressing our magnitude, instead of expressing it as r, we're expressing it as the decibel equivalent. Right, so that's why you have 20 log 10 times the magnitude of 1 upon j omega, or the log of the magnitude of 1 upon j omega times 20. This is the decibel form. All right, so if we have now a specific number for our frequency, so we're assessing the magnitude at a value, a frequency of 2 radians per second, then we could just substitute in our 2 for omega, and we have an actual number of minus 6.02 decibels. And of course, you can repeat that for various different values of omega. So you can go from lower values up to very high values. So that's what I've done in this little table. I've gone from low value of 0.1 omega in radians per second, and then 1, 2, 4, 8, 10, 100, 1,000, right? So basically what I've done is here, this part, this is the octave scale. This is getting worse. This is our octave scale, and then this one and these are our decade scale. So what we're seeing is that a pure integrator 1 upon s has behavior whereby it seems to start at plus 20, goes down to 0 at 1. If we go skip to 10, it goes to minus 20, skip to 100, minus 40, skip to 1,000, minus 60. So we can see that for every decade, the magnitude of 1 upon s equals minus 20 decibels per decade. Right? If we take the octave rule, then it seems we're going down for each octave. This is 1 octave, another, right? So for each octave, what was happening, we're going down minus 6 decibels. So I could change this and say each octave, m equals minus 6 decibels per, not decade, octave. Nice. Okay, so we've got our behavior of 1 upon s. We can see that in decades and or in octaves, in both cases, if we're using that semi-log scale, then this is actually a linear relationship. So you're going to have a straight line. This is our decades. This is a log linear plot. So our scale on the left-hand side, this scale here is linear. This is log, a log scale, right? As you can see. So this is 0.1. This is 1, 10, 100, 1,000. At 0.1, we have our value of 20. At 1, we have our value of 0. So all of these correspond to the values we had in the previous slide. As you go up another decade, you're going to have minus 20. As you go up another decade, minus 40. Right? So it corresponds to what we expected. If we just take the octaves, for instance, this is 1, this is 2, this is 4, and this is 8 here. So these all also, correspond back. Zero, this is minus 6, minus 12, minus 18. So you see the octave plots lie on the line as well, the straight line. Okay. So we've plotted our pure integrator. We determined it's a straight line. It has a gradient of minus 20 decibels per decade, or minus 6 decibels per octave. What about the phase? Now we said for the pure gain there's no phase because there's no imaginary part. This transfer function, however, the pure integrator, this is all imaginary, right? It doesn't have a real part. It's just a purely imaginary element. So what's our as our phase going to be? We'll take the argument to determine the phase lag, and the argument for a quotient. Okay, let's move on to our next factor. This factor is our first order lag. All right, so now we actually have a real part as well as an imaginary part on the denominator of this factor when we convert the factor from the S domain to the frequency domain. Let's take the magnitude of it using the same rules as before. Then there's going to be the magnitude of this term, this factor is going to be 20 log base 10 of 1 upon, or the magnitude of 1 upon 1 plus j omega tau. So we know we use, it's going to give us 1 over root 1 squared plus, well, the j squared cancels, so omega tau all squared, right? So that's what we have here. This is going to be our expression for magnitude. So if we again select a value, we could plug it in. Once we have a value for tau, and in this case, you can see that actually, I should have probably explained this before. You could also express this if we leave it in the S domain. It's going to be 1 upon 4 over 1 plus S upon 4. So that's in the same format as kind of K over 1 plus S tau, right? So we do have a pure gain factor in here from the division of, you know, from the organizing or the rearranging from the 1 over S plus A form to the K over 1 plus S tau form. Right, so we bring out this 1/4 here. That's just something to be borne in mind, right? So what we could do though is actually, so this is a kind of generic expression, but when we are specifically applying it to our transfer function, I'm going to now convert this to j omega. Our G4 becomes 1 over j omega plus 4. Right? So our magnitude of G4 j omega is going to be 20 log 10 times the magnitude of this, which is 1 over root 2 squared plus 4 squared. Right? The 2 is from omega equals 2 radians per second, and the 4 from this part here. So that gives us a value of minus 13.01 decibels. And we can do the same thing for a range of different values. I've used the same values I did before. So for this M4 magnitude of our G4 at 0.1, we have minus 12, 1 we have minus 12, 2 we have minus 13, minus 15, minus 19, minus 21. Right, so you see that it starts out with some negative value here, and that actually corresponds to the 1 upon 4 that I showed you earlier, right? So and then when you get up to higher values, let's say from 10, minus 21, 100, minus 40, 1000, minus 60. So this appears to be approaching a straight line at these higher frequencies. And the straight line appears to have a gradient of about minus 20 decibels per decade. And we've seen that before because our pure integrator, which we looked at here, is also got a gradient of minus 20 decibels per decade. So you can see that a first order lag, it doesn't behave quite like a pure integrator, but when you get to higher frequencies, it does seem to behave like a pure integrator. So if we plot these values that we just calculated, and again, this is using MATLAB, so we've got the two separate graphs, but when we're sketching it by hand, we're going to overlay them. But we can see the general shape of these curves. This is the magnitude curve. Let's not look at the phase one for now. We're just looking at the magnitude. The general shape of our magnitude plot is that it's about minus 13. This is 20, so this is minus 13 or minus 12, let's say. As we're going along, when you get to 1, this is 1 here, 1 radians per second, 0.1, 10, 100, right? At around 1, we just started to drop down, so this gives us our minus 13 that we calculated. And then it curves around, and then by the time you get to around here, which is 10, you see that we basically have a straight line going down here. So by the time we get to 100, we're going from minus 20 to minus 40. So that's our 20 decibels per decade there at the higher frequencies. Okay. Now, if we were to generalize the behavior of this and normalize the first order lag, so that's where we go from the, G equals 1 over S plus A, and we're going to normalize it by saying G equals 1 over A over 1 plus S tau. Right, so that actually equals 1 over A times 1 over 1 plus S tau. So if we normalize the transfer function, we could take out the constant part, which is what we call the gain of this particular little transfer function. So we take that out, and we have a normalized 1 over 1 plus S tau. And then our S converts to J omega because we're substituting J omega for our S's. And then we can say, well, what happens at very low frequencies for this normalized element? So ignoring the gain part of it, we're just looking at the normalized part of that term. And we can say that if we have very low frequencies, then this is going to reduce, this is going to go towards 0. So that means it's going to be 1 over 1, which is 1. And if we take 20 log 10 of 1, then we're going to have 0 decibels, because the log of 1 is 0. If we go to high frequencies, then this is going to be effectively 0, and we're just going to end up with 1 upon J omega tau. And if you take the magnitude, the J is irrelevant, so that gets eliminated. And so that's going to be equal to 1 upon tau, which is a constant, so this magnitude is just a constant term, and then 1 over J omega. This is familiar because this is our first order lag, right? So that's why, not our first order lag, sorry, our pure integrator. So that's why at high frequencies, where omega is much bigger than 1, and we can neglect this term here, then what we can say is at high frequencies, the behavior of a first order lag approximates to pure integrator. Okay, and you could also say the behavior of a first order lead, because we're dealing with a lag, but the same logic is true for a lead, and that would be approximating to the behavior of a pure differentiator. So some important links there that help us to interpret and understand how this sort of phase part of it works. Sorry, the magnitude part of it works. So then let's look at the phase part. The phase parts, again, we take the phase of the numerator minus the phase of the denominator. The phase of the numerator is 0 because there's no imaginary part. The phase of the denominator is going to be negative tan to the minus 1 of our imaginary part omega tau over 1. So of course this does have a shape to it, because tau, although constant, you multiply that by omega, and you're going to get varying values of argument. So if we take omega equals 2, for instance, 2 radians per second, then we're going to get minus 26.6 degrees. And so we could look at different numerical values again and plot them just by substituting them in to this equation here. Okay. Now this looks a bit different to this. Why is that? Because this is the normalized expression, but this one is just directly from the transfer function. How so? Just 1 second, let me try something. Well, because the argument of G4 is going to be 0, because there's no imaginary part on the numerator, minus, still doing it. I think I have to bring a new nib for my little pen. Tan to the minus 1 of imaginary, which is, in this case, just going to be I don't know why there's a 2 there actually. Shouldn't that be a 1? Because this is J omega equals 1 over J omega plus 4. Alright, yep, sorry. So we're saying our omega is 2, so therefore our imaginary part is 2. So imaginary is 2, real is 4. Okay. So that's where we get our minus 26.6 degrees. If we said, okay, if omega equals 4 radians per second, and that is actually equal to omega equals 1 upon tau, right? Because tau, for this one, we can transform this. This is equal to 1 upon 4 over 1 plus s tau. So the tau in this case is 1 upon 4. So 1 upon 4 is 4, right? So omega is 1 upon tau. We plot that, you see you get a minus 45 degrees. And that's always going to be the case. Whenever you get omega equals 1 upon tau, then you're going to get a value of minus 45 degrees for this, the phase of the first order lag. So I picked that up on the plot here just to show it, on this bottom plot for the phase plot from MATLAB. When we get up to 4, this is 1, 2, 3, 4, so at 4 radians per second, sure enough, you have minus 45 degrees. And you can see generally that as you go to lower frequencies, you're going to be approaching 0 for the phase. And as you go up to higher frequencies, you're going to be approaching minus 90 for the phase. So that's how this is formed. It's sort of an S-shape curve for the first order lag. And it's going to start close to 0, and it's going to go up to minus 90. It'll never quite reach minus 90. It basically just levels off here forever. So, and then the third consideration is it's always going to pass through minus 45 degrees. So knowing these basic shapes or forms of the Bode plots, both the magnitude and the phase for our different factors, is going to be very helpful for you when you're plotting, because you could basically make sure you're getting it right. Right, we're going to do the quadratic part now. So this, of course, is the most complex one. And our G5 is this. So how do we plot the magnitude for that? How do we plot the phase for that? And can we see some general patterns that come out of it? So same approach as before. So again, dealing with it generically, using our standard second order or prototype second order transfer function here. If we were to convert that to J omega form, to frequency domain form, then of course each of these terms gets replaced to the J omega every S. So you've got a J omega squared here, you've got a J omega here. So then you can separate out your imaginary and real parts. This becomes the imaginary part right here, and then this S equals J omega squared. J squared is -1, so that's where you get this term from. So you can combine this real part with this new real parts you get by squaring a complex. Right, so we said before, if we want to calculate the magnitude, then we're going to have to take the magnitude of the numerator and divide by the magnitude of the denominator. The magnitude of the numerator, that's straightforward. There's no real part, no imaginary part, so it's just going to be omega n squared, and then divided that by the imaginary part squared and the real part squared, and then take the square root of that. So that's what we're going to do. So the magnitude is going to be 20 log 10, because we're dealing with decibels. We want to get it in decibels. It's going to be omega n squared on the numerator divided by omega n squared minus omega. This is our real part squared, and our imaginary part squared, square root it, and that's how we get the value. Now if we take our transfer function here and we say, okay, this is equivalent to 1 upon J omega squared and 4J omega and run out of space 10, right? Then we can further reduce that. So this is 10 minus omega squared is the real part, and 4 omega j is the imaginary part, right? Or 4 omega is the imaginary part. So if we take the magnitude of that, then this is the real part, this is the imaginary part, because we're applying omega equals 2 radians per second, right? So it's going to be 1 over our real part squared and our imaginary part squared, all square rooted, and it comes out to -20 decibels, right, when you work that through. It's actually going to be a pretty small number in here, or you know, the value here is going to be smallish. And so once again, we can calculate for different values of omega and substitute those into our equation and get the values, and these can be used to plot. So we're saying at low values of frequency we basically have -20. We have -22 at 3.16, that's significant, and then it's going up from there. Now if you look at these last three terms, again you're seeing linearizing of the curve, and in fact you can even come back and look at 1 as well, and we can see that you basically have well, no, don't look at 1, sorry, that was an error on my part. No, you just look at these last three at the end. You go from -40, the next decade is -80, next decade is -120. So you can see again there's sort of a straight line here at -40 decibels per decade, -40 decibels per decade. That's different to our first order element, which is -20. Right? This 3.16 also corresponds, by the way, to omega n. Right? So that's because it's root 10. So this, ignore the phase on the bottom for now because we haven't dealt with that yet, but let's look at the magnitude plot. You can see it's straight -20, and then after, you know, around here somewhere, you can see there's a change in the slope, right, around here somewhere. So this is 1, 10, 2, 3, 4, 100,000. So you can see around between 3 and 4, the slope changes. It goes from being a steady minus 20 decibels, and then the slope changes, and now you have a slope of over 1 decade, you're going down 40 decibels, minus 40 decibels per decade. If we had a different transfer function, you might have found something like this. So I just plotted, overplotted another transfer function on this plot, and that one is shown in the green here. And when you plot that transfer function, you see a very distinctive peak at this point. Right? You notice that this is approximately omega n. Right? I just roughly sketched where the location is, but you can see that there's a kind of turning or a corner frequency around the natural frequency of that second order function, second order system. And what we're seeing here is that if you have a different function, it's actually giving a little peak, and the peak occurs around somewhere around omega n. In fact, it's at a location called omega d, or omega r, not d, which is the resonant natural frequency, but it's very close to the natural frequency. So that's something to note. You can get this little spike. So let me just finish to plot the phase element as well for this one. So just a couple more slides and then I'll wrap up. So control systems often possess quadratic factors. So we'll often have these quadratic factors in our transfer function, our open loop transfer function. We need to be able to plot them using Bode plots. And if this is our generic form, which we dealt with last time, we're going to derive this generic form for our second order system in frequency, in the frequency domain. Then the magnitude of this fella is going to be given by this, and we can see again certain properties that for low frequencies where omega is much less than omega n, this is going to 0. Right? This is going towards 0 as well. So you're going to have at low frequencies 0 decibels basically, because you only have a 1 left over, and the log of 1 is 0. But if we do the converse and say, what about at high frequencies, right? So when you've got a very big omega, it makes omega n less relevant compared to the size of the omega, and you can basically say that, well, what we could also say is that this term here, oops, I seem to have lost my pen, right? This term here, because this is omega over omega n, that this is omega squared over omega n squared. When you go to a high frequency, then this omega squared is obviously going to make this term much more dominant. The 1 becomes irrelevant, but this term becomes dominant. You square it. This effect kind of will approximate down to 0, and this goes to, this is irrelevant. So you just end up with this term here. So you squaring it, and then you're square rooting it, so the square and the square root cancel off. So you end up with omega squared over omega n squared. You're taking 20 log base 10 of that. But the log rule says log of x squared equals 2 log x. So we're taking the squared term here, and we're putting it here. It's the constant, so that will give us minus 40 log 10 omega over omega n. Right? And that's where we get our minus 40 decibels per decade gradient from, that we saw on the last slide, not the last slide, this slide. Right? This is our minus. And at the special case where omega equals omega n, then we got another set of sort of particular behaviors. But basically, this, if this goes to omega n, then this will be omega n over omega n. This is 1, so 1 minus 1 is 0, so this goes to 0 for omega equals omega n. And then this will go to 1. So we got 2 zeta squared, square root it, it's 2 zeta. So at that frequency, of natural frequency, then the magnitude is going to be 20 log 10, 1 upon 2 zeta. So if you have a small value of zeta, or in other words, a low damping ratio, then this is going to get bigger, and you're going to, that's how you get a resonant peak, or a peak magnitude at this resonant frequency, which is not quite at the natural frequency. It's a small shift away, but this is where we get, you know, shows mathematically we're getting a potential peak. And our peak is going to be 20 log 10, 1 upon 2 zeta. And the actual resonant frequency it occurs at is omega n root 1 minus 2 zeta squared. Right? And then after that, you can see that the line converges to the minus 40 decibels per decade line, which is the gradient as the frequency goes up to infinity. Or if you want to be more precise, you could actually give a slightly more precise expression for omega, for MR, which is this 20 log 10 of 1 over 2 zeta root 1 minus zeta squared. So basically, you know, for small values of zeta, this is going to be pretty small, and then it'll just be dominated by this term. Now, when we're talking about phase, one thing that we have to keep in mind is that we're taking inverse tangents of to get our phase, right? I said that the angle, or the argument of our complex number z, is given by the inverse tangent of the numerator imaginary over the numerator real minus the inverse tangent of the denominator imaginary over the denominator real. Now, we're taking inverse tangents. You have to remember what the tan curve, or the set of curves which are the tangent function, look like, right? So the most obvious characteristic is that at about every 180 degrees, at minus 90, then plus 90, then at 270, you have these discontinuities, right, where the tangent curve is going off to infinity, or on the, just as you cross this this asymptote at minus 90 degrees, for instance, then you go from plus infinity effectively is your out, is the tangent of your angle, to minus infinity as you just cross over this discontinuity at minus 90. So this side, you're at about, you know, let's say we're right here, you know, we've got a comfortable 4, and if we cross over, just slightly come across this side, then we're going to be at minus 4, and there's a discontinuity between those two values, right? So we have to be conscious of that when we're using tangents, because what we might find is that we are close to a discontinuity in our calculation when we're taking the inverse tan, and we might just skip across if we're not careful. So we have to bear in mind how this tangent function looks, and that you've got a minus 90 of discontinuity, at minus 270 of discontinuity, etc. So what's the tangent in each of these cases? What's the inverse tangent of 1, for instance? Anybody? Pretty easy. Just stick it in your calculator and you get it. Yep, 45 degrees, right? So A tan D of 1 is 45 degrees. So we could actually say, well, 1 is around here somewhere. So, you know, I'm tracking across. I actually have in the range of values from minus 360 to plus 360. I have 1, 2, 3, 4 solutions to that calculation. All right, but the one that you identified is this one, because that's what your calculator will tell you. But you could equally have minus 135 degrees. It's equally true. You could equally have minus 315 degrees, right? Or you could equally have what's this? This is 215 degrees, I think. Right, so all of those are solutions to that particular problem, right? Of inverse tan of 1. You could do the same for inverse tan of 8, which is here, right? And you could get a solution which is oftentimes, in fact, what you'll do is you'll get this solution here, because your calculator will default to give you that solution, and that's going to give you like about 88 degrees or something. I could try it. Well, 83 degrees, right? It's going to give you 83 degrees. But we're probably, you know, you have to just bear in mind that you could also have a value here, right? The same story. And this is going to be 96 degrees or something. Then the same thing for minus 1. Minus 1 will be down here. So if we take the inverse tan of minus 1, then we're going to get minus 45 degrees. That's coming from here. But because it's the negative of the inverse tan of minus 1, then we're actually going to get plus 45 degrees. Beg your pardon. It's going to be plus 45 because it's the negative of that, right? So the answer on the tangent curve is minus 45, but the negative is plus. And so just remembering that, just keeping that in mind when we're looking at the calculating phase. So for our phase, we substitute S equals J omega again, and now we're using our expression for the phase, inverse tan of imaginary over the real of the numerator, minus inverse tan of the imaginary over the real of the denominator. Now, of course, there's no imaginary part here, so there's a 0 on the numerator of this inverse tangent. This goes to 0. But this one, you know, of course, we're going to have a value. So we're going to get minus tan to the minus 1 of something, which should depend on the values of our zeta, our natural frequency, and the value of omega that we're using, right? So if we have values of zeta and omega n of 0.4 and 3, for instance, then for these conditions that I've specified here, we'll be taking minus tan to the minus 1 of 2 times 0.4 times 3 omega over omega n squared is 9 minus omega squared. Okay, so if we say omega equals 0.1, what's that going to give us? So just substitute in 0.1 here and 0.1 here. you can see 0.1 squared is going to be 0.01. So basically this goes to 0 when you have a small value of omega like 0.1. The 0.1 here is going to have an impact. So it's going to be 2 3s are 6, 6 4s are 24, 2.4 times 0.1 is 0.24 on the numerator. So that's going to be minus 10 to the minus 1 of 0.24 over 9. Right, so if we calculate that, then we're going to get a very small number. Right? In fact, when I just typed this into MATLAB, I got 1.5 minus 1.57 degrees. Right? So this is close to, approximates to 0. It's kind of close to 0. If we go to omega equals 3 now, so we would, now this is no longer approaching 0. We've got a 9 here, because it's 3 squared is 9, so 9 minus 9 is 0. And you have a 9 here. So even though this is a significant number, 9 minus 9, that goes to 0. So in fact, 2 3s are 6, 6 4s are 20, there's 2.4 times 9, which is 21.6. But it's going to be over 0. So now that's giving us an infinite value for we're taking the inverse tan of an infinite value. But the nice property about tangent curves, as we just looked at on the previous slide, is that you can actually have a value for an infinite input, right? So where inverse tan of we're taking the inverse tan of infinity, then well, we can see that that could be here, it could be here, right? So there are actual solutions for inverse tan of infinity, right? That being minus 90, plus 90, etc. So in this case, our phase is going to end up being minus 90 degrees. For this one, phase equals 0. Well, let's say it's minus 1.6, I think. What about when omega goes very large? So we're just learning about how this behaves. When omega goes very large, to 1,000 for instance, what's going to happen? We're going to have 1,000 on the numerator here, and we're going to have 9 minus 1,000 squared here. So of course, effectively, the 9 goes to 0, and because you've got 1,000 squared on the denominator, then all of this, even though you've got 2,400 on the numerator, you have effectively got a million on the denominator. So that's approximating to well, it's about 0.024, right? So it's close to 0. So what's the inverse tan of 0? I guess we could go back again. The inverse tan of 0, that brings us to a 0. But this is where we have to be careful. It also gives us plus 180, and it gives us minus 180. Right? So you have to be careful which you select. In this case, you'd want to take this one, the plus 180. Because if you take the plus 180, then that gives you phi equals minus 180 degrees. Right? Otherwise, if you take the 0, that's not how this phase line actually flows. So you do have to be careful, and this is the point I was making by sort of showing those tangent curves. But what we're identifying here is a second order also has a standard shape. It looks like this. This is what you'd call asymptotic approximation, because it just has straight lines, it hasn't got any of the curves to it. But asymptotically, you have 0 phase up until omega n upon 10 zeta, and then above that you've got minus, you've got a line comes straight down going through omega, at omega n, the natural frequency, you've got minus 90, continues down to minus 180 at about 10 omega n zeta. Right, so you've got key values or key parameters on our curve. So let's find the actual phase for the value for the G5 term in our transfer function. Now, first of all, we can calculate our omega n. Omega n is 3.16 radians per second. Comes from this term from the first order. Remember, again, the first order prototype transfer function. Right? So our omega n squared here equates to our 10. So then omega n root 3.16, and then we can calculate from that. We know that 2 zeta omega n is 4. That's this term here. So we can calculate our value for zeta, 0.63. So we have values for omega n and zeta. So now we can sort of plug them in into our phase calculation. Of course, again, this is 0, but the second term is a function of omega on the numerator and the denominator. So we actually have to calculate it. If we calculated it and plugged in different values for omega, 0.1, 1, 2, 3.16, 4, 8, 10, etc., etc. If we were to calculate it, then at omega equals 0.1, then you're going to get minus 2 this shouldn't be decibels, sorry. This should be degrees. The phase would be minus 2 degrees. At 1, put 1 in here and here, you get minus 24. At 2, again here and here, you get minus 53. This one is significant. This 3.16 is our natural frequency. So as we said on the previous slide, at our natural frequency we expect to see minus 90, and yes, we can verify that because we are seeing minus 90 at 3.16. And then as we continue, we go up to higher numbers, you get minus 180 as expected from our asymptotic approximation. Yeah, we go down to minus 180 here. And if we plot these values now, we did calculate both our magnitude for this particular term, this G5 term, the quadratic lag that we have in our transfer function. Then we get 0 decibels, no, sorry, minus 20 decibels up to around the corner frequency, which is around the natural frequency. All right, instead of turning at this point. In fact, the natural frequency is right here, I think. Yeah. 1, 2, 3. Sorry, it's right here. Yeah, that makes sense. This is 3.16, right? So up until the natural frequency, we have 0 on magnitude, and then it comes down at minus 40 decibels per decade. This is 1 decade here after the corner frequency. This is another decade here. And each decade we go down minus 40 decibels per decade. Right, and this is around omega n here. Our phase plot starts at 0, ends at minus 180 as we expect, and No surprises, at minus 90 it goes through omega n. Now we have put together our G1 is black, that's this constant gain, right? I wrote it in red. It has no phase contribution. Then you have G2, which is your pure, that's the first order lead. You can see it coming fairly level, then it curves up at 20 decibels per decade as the frequency increases. And you can also see the phase lead here. It goes from 0 to plus 90. Then G3, that's a pure integrator. It's coming down minus 20 decibels per decade on this on the magnitude plot, just this orange line, minus 20 decibels per decade. The phase, it has minus 90 contribution right through. G4 is a first order lag, so that's coming along and then going down at minus 20 decibels per decade above the corner frequency. It's starting at 0 on the phase and it drops down to minus 90 on the phase, and it passes through a phase of minus 45 degrees at 1 upon tau, the time constant for that first order lag. And then finally we did G5, which is shown in purple. That's the second order lag. So it starts out here around the corner frequency of omega n, starts to come down at minus 40 decibels per decade. And for the phase, starting at 0 for the purple line, which is our second order lag, starts at 0, comes through minus 90 at the natural frequency of 3.16 radians per second, and it goes on to a high minus 180 degrees as you go to high values of omega. So what I've done now is I've just plotted, I've sort of taken off all the different color lines here, just focused on the green one, which is the total, because once you've got all these different colors you can nicely add them up and plot the total line. So the GOL I have here, this green thick line, this is the total values for the magnitude, and on the bottom the total value for the phase. So I'm plotting just those green lines, they turn blue. So now we're going to take note of something we're coming on to in just a minute, or a little bit later on, let's say. You notice that we have what's called a GM and a PM here that we got from plotting our Bode plot in MATLAB. And these are our gain margin and our phase margin. Now, if we want to know how to calculate them, you calculate, and we'll come to this later, but I'm just preempting. If you want to get your gain margin, you have to look at where the phase line crosses minus 180 degrees. That's why this dotted line goes up from there. It intersects the gain margin here at minus 28.7 decibels. So basically that means you could add this much 28.7 decibels of gain to the system before the gain line crosses 0 dBs at the same frequency as the phase line crosses minus 180, and that is the condition for marginal stability when interpreted by in the Bode plot or the frequency domain. You also see that we've taken a line from where the magnitude plot crosses 0 decibels. We've taken that down to here, and we've called that distance between the value of the phase where the gain line crosses 0 dBs and minus 180 degrees phase. We've called that the phase margin, and as we can see here, the phase margin is 89 degrees or so, as is stated at the top here. Right, so our phase margin is 89 degrees. Technically what that means is you could add 89 degrees of phase lag to your system before the system becomes marginally unstable. So again, at 0 decibels, that occurs at 0.15 radians per second on the frequency axis. Right, and then if you track down, you get the location of your gain margin. If you find the value where the phase line crosses minus 180 degrees, then you track up. That will give you your gain margin. It's the gain you have in hand at that frequency. Okay, so we're going to go through some examples now. So this is our first example. Construct a Bode plot for this system. The system transfer function, or the open loop transfer function, is K times 2 over S into S into over 2 over S into 1 plus S upon 2. Right, so this one we can see immediately it's a first order type 1 system, and we're going to plot the magnitude plot for this, and then we're going to plot the phase plot. And when we plot using, when we construct our frequency response plot or our Bode plot, we're plotting open loop frequency response, and then we're using that to analyze closed loop stability. And we always go through the process of splitting down our open loop transfer function into parts or into factors, and we're going to create or determine the magnitude for each factor separately. We're going to determine the phase for each factor separately, then we're going to add them back together, and then we can plot the overall frequency response. So let's look at the magnitude plot first. We are converting our S or Laplace S domain transfer function into a frequency domain transfer function here. Then we're splitting up our transfer function into individual parts, and then we're going to do the analysis for each part, and we're going to put them back together. It's a second order transfer function additiva. It is a second order, but this type of second order is actually referred to as a first order type 1, because you have a first order lag and you have a pure integrator. It's second order, but it's called first order type 1. Sorry for the confusion. Don't blame me. I didn't call it that. Alright, so these are our factors. We could probably label them just to make it clear. Well, we're gonna we could label 1, ignoring the K for now, 2 and 3. Right, so the first factor, factor 1, is pure scalar, a loop gain of 2. So that'll have no phase component at all. But it does have a gain component. The gain component is again simple. Just take 20 log 10 of the value, which is 6 decibels. That gain will be a constant gain across the entire frequency range. So that's just like a factor that's included there. Our pure integrator, what's going to happen with the magnitude plot for a pure integrator? Well, pure integrator always has minus 20 decibels per decade on the magnitude side, and it goes through 0 dBs at 1 radian per second. So this is going to be the plot of that term 2, the pure integrator. So straight line for magnitude going down through 0 decibels. 0 decibels at 1 radian per second. Yep. And then we've got a first order lag here. So below the corner frequency, then you'd expect 0 decibels. Above the corner frequency, you'd expect minus 20 decibels per decade. The corner frequency is going to be 1 upon tau. Tau in this case is 1 upon 2, so that's going to be 2. So we have 0 decibels up to our corner frequency of 2, then we have minus 20 decibels per decade after that. Now this is, again, plotting an asymptotic approximation. So this isn't, it doesn't take into account certain curves and so on in the plot. So we have to do that. We have to round it off before it gives an accurate representation. So when we can do that by determining what the value of magnitude at omega equals 2 is, and then we can plot it precisely. So let's do our magnitude plot. I can fill in the table. So our first element, our pure gain. Our pure gain is just going to be, it's going to take the log of it and multiply it by 20. And the corner frequency is the frequency at which there's a kind of a point of inflection in the magnitude plot. So you're going to get from your pure gain, it doesn't matter what your frequency is because there's no frequency term in here. It's just going to be a constant of 6 decibels. What about our pure integrator, 1 upon j omega? Well, that gives us a magnitude of 20 log 1 over 0, because there's no real part, plus omega squared. That's our imaginary part. So that's just going to be 1 upon omega, right? It's going to be 20 at 1. We're going to be at 0. At 2, it's a minus 6. At 5, we're at minus 14. At 10, this is 10, it's minus 20. And at 100, we're at minus 40. Right, so we've got our magnitude for that. When you're doing this in an exam context, of course, you're going to have to plug in number by number. But I'm using MATLAB for expediency in this situation. Right, next term. So this is our first order lag. That was pure integrator. That was pretty easy. That one is just a straight line. What about our this first order lag? Well, let me enter this one into MATLAB as well. So I'm going to call this M3 equals 20 and log 10 of 1 over square root of 1 plus, I think I have to do my dots again. Every time you have an array, because I've called omega, I've made this into a matrix or an array, you have to use the dot slash format, because what that does is it tells MATLAB to multiply term by term instead of trying to treat it as a matrix multiplier. It's omega squared upon omega upon 2 all squared, right? Omega upon 2. We have to use it for power as well. All right. Okay, so this is M3. So basically, you see for the low values of omega, in 0.1, 1, 2, 5, etc., you see we're basically at 0. When you get to the first two, 1.1 and 1, when you get to 2, you get minus 3 dBs. And then as you go up to 5, you get minus 8. Sorry, this is 2. 0.1, 1, 2, 5, 10, 20, 100, right? So yeah, what we're seeing is a fairly much close to 0 up to this thing called the corner frequency. The corner frequency is defined as 1 upon tau. So this term is 1 upon s upon 2, so tau is a half. So 1 upon tau. So this is 1 plus s tau, where tau equals a half. So that means 1 upon tau equals 2. Right, so our corner frequency, as we said, is going to be at 2. We're going to have minus 3 dBs. At 0.1, close to 0, so just rounding up. At 1, we get minus 1. At 5, we get minus 9. At 10, minus 14. And at 100, minus 34. Right, so now we can add these up. 26, 5, minus 3. Is this minus 23 plus 6 is minus 17, I think. This one is going to be minus 34. It's minus 28. All right, so we're just adding these up quickly here. It's 474 is minus 68, I think. Right, so I've got my sums right. There are the answers. So we've got our plot for our magnitude there. We've got our values for our magnitude at different frequencies. So now I can draw that here on my semi-log paper. This is our magnitude in decibels here. So this is decibels on the left side. Now on the right side, we're going to have our phase line. Use a ruler when you do yours. This is degrees, and we're lining up 0 dBs with minus 180 degrees. So log omega here. So I'm going to start with 0.1 on this first scale. Now, if you look at the bottom, you see these numbers. So this tells you, this gives you your logarithmic scale for omega. So this is going to be 1.0. This is going to be 10. This is going to be 100 here. Right, so at 0.1, I start off my plot. I've got a value of 26 for my magnitude. That's here. At 1, I've got a value of 5. And so minus 3 is just about here. Minus 3 is here. At 5, minus 16. 5 is here. I'm taking you through this so you can get a sense of how to plot the thing. Right, and then minus 28 at 10. So it's coming down fast. You can see how the line is starting to bend downwards. And then minus 68 at 100. Right, well that's off the bottom. I've actually not got enough space on the bottom here, so I have to come down here somewhere. My pen is really misbehaving. I don't know why it's doing this. So there's my gain plot, as best I can do using this sort of computer drawing thing. Right, so let's do the phase plot now for this example. And are interested in particular a stability analysis, which is what we're coming to with the gain margin and the phase margin. It will involve looking at the gain plot in the region of 0 dBs and the region of -180 phase. In computing the phase angles, therefore, we want to choose frequency values that give phase angles in this region, right? So we're looking to kind of get phase angles around -180 ideally. Now, in this case, not every case you'll get to -180. So let's see what happens here. The maximum phase you get, negative phase, will actually be -90 times the overall order of the transfer function. So let's go through and calculate our phase lag. The first one is easy because it's a pure gain. A pure gain doesn't contribute anything to our phase lag. So these are zeros right through. We've got a pure integrator. A pure integrator, you see there's a 0 on the denominator because there's no real part on the denominator of our transfer function for this element. There's a 1 on the numerator, no imaginary part, so you have 0 minus down to the -1, right? So the numerator doesn't have any phase contribution, so 0 minus the phase contribution from the denominator. The denominator only has an imaginary, not a real part, so the imaginary is omega, the real is 0. Therefore, this goes to, of course, infinity. And if it goes to infinity, we then know, okay, this is going to be -90 right through, based on the characteristic of our tangent plot, of our tangent function. Right? Now, our first order lag. The real part, the numerator has a real part, no imaginary part, so it's 0 for the numerator angle or phase, minus the phase of the denominator, which is imaginary over real. The imaginary part is omega upon 2, the real part is 1. So we can calculate this one now for each of our phase values. So switching back to MATLAB, so 0.1 is -3, 1 is -27, -3, -27, 2, right? So -45 for our corner frequency, right? Remember, this is the frequency. 2 radians per second is 1 upon tau for this element. Then when we go to 1.1125 is -68, 10 -77, and 100 -89. So we're going to add these up. Now I'm going to use this, do my phase plot on here. So we've got -93, 107, 135. Right, so it starts out here, and we know the shape of this curve is that it's going to come like this. Not perfectly drawn, but you get the general idea, right? So you can see that the a characteristic is that even though it looks like it does based on my drawing, in fact, based on the numbers, we can see this does not cross -180, but it converges to -180. And we said this is a second order type function, so expect it to the phase to go to -180 and not to go beyond that. Let's do our next example. This is our new system. So what's the open loop transfer function for this? So that's our open loop transfer function. And we're going to have 3 elements, which is going to be 10, 1 upon s, sorry, 4 elements, and then 2 first order lags. Element 1, element 2, element 3, and element 4. Right, so if I do switch to MATLAB, first of all, M1 equals 20 times log base 10 of 10. That's 20. So we know the first element there is going to give us 20 decibels throughout our frequency range, and we're not going to have any phase contribution from that. From our pure integrator, well, the pure integrator is exactly the same as the previous example. Our previous example, we saw a pure integrator gave us a straight line in gain, starting at 20 decibels at 0.1, going through 0 at 1 radian per second, and minus 20 at 10, minus 40 at 100. So it's minus 20 decibels per decade, going through 0 decibels at 1 radian per second. So that's that one. This one, well, we can calculate or get our magnitude plot for this. You're going to go to MATLAB. M3 equals 20 times log 10, and our numerator is just 1, so 1, and our denominator is going to be 1 squared plus 0.2 omega, right? So one of the things I should have done here is I should have converted this to j omega form. So in j omega form, it's going to be 10, 1 over j omega, still doing it, 1 over 1 plus 0.2 omega j. Now this is going to be 1 over 1 plus 0.05 omega j. Right, so for this M3 part in MATLAB, it's going to be the square root of 1 plus 0.2 times and omega squared. I forgot to put my dots in front of the right. So that's our magnitude for M3, and M4 is going to be 20 times log 10, 1 over 1 dot over square root 1 plus 0.05 and omega dot squared. Right, so again, root sum squared of the numerator over the root sum squared of the denominator, and then we're expressing it in decibels, which means you take 20 log base 10 of that value. So there's our values for our M3 and our M4. We already got our value for M1, and I'm going to do another kind of cheat here. We said M2 is 20 times log 10 1 over omega, right? And M1 we said is 20, but I want to add these up. But M1 is just a scalar number, so I need to make it into an array. So I'm going to multiply it by how do I do this again? There you go. That little function there to pick up. So the overall magnitude M is going to be M1 plus M2 plus M3 plus M4. So that's our overall magnitude values, right? For this, the first term is 40. Next term at omega is of 1 is 20. Yep. Next term 13. Yep. Next term is 2.7. Next term at omega is 10 is minus 8. Omega 20 is minus 21. And omega 60, omega 100 is minus 60. Right, that's this term. Good. So we've got our magnitude plot there already. What about our phase? Let's deal with our phase. And I'm going to do the same thing using MATLAB to get our phase values for these. So, well, we already know there's not going to be any phase contribution from a pure gain. That doesn't contribute to phase at all. Our pure integrator, we know that's going to be minus 90 right through. A lot of minus 90s. Right? Our first order lag, we know it's going to go from 0 to minus 90. It's going to go through minus 45 degrees at the corner frequency. Now, what's the corner frequency for this term? This is 1 upon, this is 1 plus s tau. So tau is 1 upon 5. So our corner frequency is going to be 5. So expect minus 45 degrees here. At low values, you expect 0. At high values, you expect minus 90. Right? So just approximating what we expect. And again here, this is 1 plus 1 upon 20 times s, or when we convert it to frequency form, 1 plus 1 upon 20 times j omega, right? So our, what's our time constant tau? Tau is going to be 20. So in this one, at tau, at 1 upon tau, no, sorry, tau is 1 upon 20, so 1 upon tau is 20. So 20 radians per second, we expect minus 45. You know, we're kind of going to about minus 90 when you go up to 100, and at 0, you expect at 0.1 low frequencies, you expect 0. Right, so let me go back to MATLAB and calculate it in MATLAB and see how it comes out. So P2 is my P1. I don't need to worry about that, it's pure gain. The P2 is I'm going to do the same thing I did with my M1 before, and just create a matrix that has all minus 90s in it. My P3 equals, let me do A tan B. I'm going to do it in the full format, which is the taking the angle of, or the argument, the phase of the numerator over the phase of the denominator. So this is going to be, the numerator is 0. It may throw an error here actually, so I think it might not like that, but let's see if it works. Over real, imaginary over real of the numerator, minus imaginary over the real of the denominator, that's 0.2. Over the real is 1. Okay. See if that works. 0.2 times W over 1. Alright, it worked. It gave us our values for P3. And do they line up with what we expected? Well, this is 0.1125, so at 5 radians per second we've got minus 45, right? That's good. It's close to 0 at 0.1, and it goes close to minus 90 at 100, so we're pretty happy with that. And then P4 is going to be like P3, but instead of 0.2 we're going to do 0.05, and that's gives us that one. So now our overall phase is going to be P2, remember there's no P1 because that's 0, plus P3 plus P4. So those are our values. So I can write them in the totals here. Minus 91. I round up to the nearest degree. I don't go to decimals, and I would suggest please do the same thing when you are doing your solutions. Really, because you're plotting it. You're doing this to plot on the graph, and you can't plot decimals. Obviously, I mean it's hard enough to get within sort of 2 or 3 degrees. So just use sensible numbers and sensible rounding when you're doing this. And look, we've got a value at 10 of minus 180. So that's useful because that's going through, that's where that minus 180 figure, we always want to get some value for phase around minus 180 because that's where we'll measure, from there we'll measure our gain margin. Minus 256. Let's see if these line up with what I prepared earlier. Yep. All right, we got the same numbers. Great, that's good. So now we can plot. Right. So I'm thinking I might not plot it because just in the interest of time. This is one I prepared earlier. Right. Again, apologies for the scrappiness. I think I did this in an old lecture at some point. But these are our gain values that we calculated. 0.1 was at 40. 1 is at 20. Right. 0.1, 40, 120, 213, 2.7 at 5. So this is what it looks like. 40, 20 at 1, 13 at 2, 2.7 at 5 here. We get the crossover point here. Right, so the green line is our gain plot, just plotted them and joined the dots. Likewise with our phase, which we just calculated, starting at minus 90. And then we come down, we got a value of minus 180 at 10 radians per second. And then it levels off. In fact, this time you can see it's actually going to, I could augment this plot a bit and show you that it would. This is 240, 250, 262, so minus 270 degrees is here, and this graph will level off like this to minus 270 because, like we said before, it's a third order. Right? Overall, it's a third order function, so the third order function is going to level off at minus 270. Right, now, what we've done here is now we've got a gain margin crossing 0 dBs, and we also have a phase line crossing minus 180. So, because the phase line crosses minus 180 at the point at the frequency where this phase line crosses minus 180, which seems to be about, yes, it's 10. Well, we just calculated that is 10 radians per second. What's the magnitude at that point? And the magnitude we calculated, I'd say maybe about minus 8 decibels. So you could move this green line up by 8 decibels before the magnitude line, the green line, crosses 0 dBs at the same frequency as the phase line crosses minus 180 degrees, right? If you do that, then you've got 8 decibels, 9 decibels in hand. That's your gain margin. So this is your gain margin. And you could also add this much. If you look at where the gain line crosses 0 decibels, you could move the red line, the phase line, down by about 18 degrees, right? Before the phase line crosses minus 180 degrees at the same frequency that the magnitude line crosses 0 dBs. So you have basically 18 degrees of phase lag you could add to the system before those two cross at the same point. That's your phase margin, 18 degrees. If you added 18 degrees of phase lag and they crossed at the same frequency, then that system would be marginally stable. And if you crossed it and they went further, it become unstable. So this is our stability measure. So here is it plotted by MATLAB just to show us on the right track. So let's come back to look at how do we actually calculate these parameters I've been talking about, which are gain margin and phase margin. Now, what we're going to start with is looking for a property or a criteria associated with open loop frequency response that we can relate to closed loop stability. So we plot the Bode diagrams based on our open loop frequency response. We take the open loop transfer function, and remember that the start of this series I was showing you a diagram where we're feeding a sine wave as our input into a system, and as our, let's call this x and y, as our outputs we're getting a corresponding sine wave. And if we compare the two, then what we find is that we might have an input sine wave like this and an output sine wave, you know, kind of like this. So you notice it has a larger magnitude and it has a slight phase shift here, phase shift phi. Oh shucks, I can't undo. So let me just plot this again. Right. So it has this phase shift phi, and it's got a different magnitude, right? So we talked about the fact that there's a relationship here. Now, if we're going to have, that's the open loop frequency response, and we want to relate that open loop frequency response, which is the relationship between the input sinusoid applied to a system and the output sinusoid we get from the system. We want to link that or relate it to the stability of the system. So if we have a closed loop system like this, imagine R is an input frequency, right? Or we apply a step input to our, let's say we apply a transient input or a step input at R, right? But after that has been applied, our system becomes marginally stable. What does that mean? It means it now oscillates in simple harmonic motion. Right? What does it take for the system to oscillate in simple harmonic motion once it's been triggered by some input? Right, so first of all, once that input triggers the system, if it gets into marginal stability, then you could basically forget about your input because the system is now oscillating in a marginally stable condition without the need for any more input. Right, so if we think about what's going to be happening here, the stability of the loop will not be affected by our input, so we can just set our input to 0. And if we assume that due to a transient response, you know, the output Vt appears, so you're kind of triggering this thing, we're starting this system oscillating. Now the Vt signal is fed back, of course, through beta, and it's switched, so it has a negative, and then through A, and comes back out here, right? So the system is circulating around our open loop. And what's going to be the output? So let's say as it comes here, we've got Vt, then it's going to be here, after it's gone through this block, beta Vt, after it's come through here, minus beta Vt, and after it's come through here, A minus A beta Vt. Right, so after going through a loop, our VT becomes minus a beta VT. So if the system is getting into this state of marginal stability and it oscillates continually or continuously, then the signal, the output signal, must be regenerated by the loop dynamics. That means that the regenerated signal, or the signal that comes out after it's been right through the loop, the signal that comes back out, has to be the same as the signal that was already there, because the system's marginally stable. That means it's continuously cycling at in the same conditions. So that's a fundamental requirement for a marginally stable system, that the regenerated signal, having gone through our blocks, is the same as the original system, the original signal. And there's only one value for minus a beta, which could mean that this is true, which is that a minus a beta has to equal 1. Of course, so if you want to, you just divide both sides by VT, right? So minus a beta equals VT over VT equals 1, right? So minus a beta has to equal 1. Now, a beta is the open loop gain, and you know, we are used to getting our open loop transfer function. The open loop gain is just the real part of that. But in reality, of course, it's not just real. It's not just the gain, but a and beta as transfer functions are complex quantities. So they don't only add gain to our signal as it passes through them, but it also adds phase shift, phase lag, phase lead. And in addition to that, when our signal goes through this negative summing block, it flips signs. That means effectively it goes from being positive to negative, or in other words, it acts as a 180-degree shift, phase shift on the system. So we've got this negative 180-degree phase shift from the summing block. We've got a beta, which is the gain of the system. So we've got two conditions that are required for this marginally stable condition to be true. One is that the magnitude of a beta, the gains, have to equal 1, and also the argument of a beta has to equal 180. So there has to, a and beta, those two transfer functions, you know, together, they have to shift the phase of the system by 180 degrees. If you add the 180 degrees phase shift from the signal passing through those two blocks to the 180 degrees phase shift that comes from the negative feedback summing block, that gives a total phase shift of 360, or in other words, the phase is synchronized back to the original phase. So now our signal, which comes from our output after it's gone through beta, flipped here back through a multiplied by a, the output is now fully synchronized. It's the same as our original input, right? That's the basic premise. So the system is shown to be marginally stable when these conditions are true. The magnitude of a beta is 1 and the phase shift is 180 degrees. Where those two conditions are true at the same time, then the system is marginally stable. So the system is shown to be marginally stable when the magnitude of the frequency response is 1. Now, if I take 20 log 10 of 1, that equals 0 decibels. So if I want to express my magnitude in decibels, then I'm taking 20 log 10. The gain is 1. So I get a magnitude of 0 decibels. So the magnitude of the frequency response is 0 decibels at the same frequency at which the phase shift is minus 180. So this brings us back to our Bode plot. So our marginally stable condition occurs when this is true. When we have a frequency at which our magnitude is 0 decibels, and at the same frequency our phase is minus 180. In other words, our phase line goes through 0 dBs at the same frequency as our phase line goes through minus 180 at the same frequency as our gain line goes through 0 dBs. So you actually have a crossover point of both of these at the same frequency. Now, when that's true, then we don't have any gain margin. We have 0 decibels gain margin and 0 degrees phase margin. So the conditions required to achieve this marginal stability may be modified to assess the relative stability. So we know marginal stability occurs when you've got this crossover of minus 180 for phase and 0 for magnitude at the same frequency. We know that's marginal stability, so that's our kind of outer limit. But we could have a condition whereby we could add a certain amount of gain to the system before it becomes marginally stable. And the amount of gain we could add before achieving marginal stability is called the gain margin. But we could also have a situation where we could, instead of moving the red gain line on this plot up and down, we could move the green phase line up and down. And we do that by adding or subtracting phase lag. So the amount of phase lag in hand before we achieve this condition of marginal stability is called the phase margin. So if we're moving the phase line down, for instance, then how far can we move it before it crosses minus 180 degrees at the same frequency as the gain line crosses 0 dBs, which is the marginally stable condition. And these measures, the gain margin and the phase margin, these two measures, they tell us not only whether the system is stable, and if they're positive values, the system is stable, but also how stable is it. The smaller the values in each case, the less stable the system. So if I want to calculate my gain margin, I have to, first of all, determine where does my phase line cross minus 180. So I have to identify this point right here, as I've labeled omega CP. And that is the crossover frequency for my phase, the omega frequency crossover of my phase line. Once I've determined my frequency at which this crossover takes place, I measure, what's my gain or my magnitude at that same point, for MC. Right, so my magnitude, I measure it off at that frequency. What's my magnitude? What's my gain? That particular frequency. So to determine the margin, if I've got a gain of, say, if MC equals, let's say, minus 6 decibels, that implies I could add 6 decibels of gain. I could move this line up by 6 decibels, right, before the gain line crosses the 0 decibels level at the same frequency, omega CP, right, as the phase line is crossing minus 180. So that is my critical condition. So my gain margin, if my magnitude at omega CP is minus 6, my gain margin is 6 decibels, right? Or if it's minus 5 dBs, my gain margin is 0 minus 5 or plus 5 decibels. So if you can move your gain line up on the Bode plot before the marginally stable condition becomes valid, or before the system becomes marginally stable, and you get those two crossover points at the same frequency, then you've got a positive gain margin. If you have to move your gain line down to get the crossover at the same frequency, that means your system is currently unstable. and you have a negative gain margin. In this case, if we have a positive gain margin like 5 decibels, that means the system will tolerate an additional 5 decibels of gain before becoming marginally stable. So looking now at the phase margin, how do we measure our phase margin? Well, our phase margin is how much phase lag can we take out of, or can we add to the system before it becomes marginally stable. So first of all, we find what's our gain line crossover, which I've labeled as omega CG. So the frequency at which our gain line crosses over goes through 0 decibels. I can move this phase line down by this much before it crosses minus 180 at the same frequency as the gain line crosses 0 dBs. How much is this? Say this is 20 degrees. Implies my phase margin equals 20 degrees. If I can move my phase line down before the crossover points are at the same frequency, then I have positive phase margin. If my phase line is below my gain margin and I'd have to move it up before we get this coinciding crossover frequencies, then it's a negative phase margin. And guess what? Your system is already unstable. So determine the phase at omega CG, subtract minus 180 from this phase angle to get the phase margin. So if omega CG, like I said, is minus 160 degrees, then the phase margin is minus 160 minus 180, so you get 20 degrees positive phase margin. This means that the system could tolerate an additional 20 degrees of phase lag before becoming marginally stable. So we have 3 conditions we could plot. A stable condition where you could move your gain line up before it becomes marginally stable and the crossover points, crossover frequencies coincide. You've got a marginally stable condition where the crossover frequencies are coinciding. 0 dBs occurs at the same frequency as minus 180 phase. And then this situation is not good because now the gain line crosses at a higher frequency than the phase line, which means that at the phase crossover point, you'd have to subtract gain to get the gain line to cross over at the same frequency as the phase line goes through minus 180. Or if you do it the other way around and say, where does the gain line cross? That's my omega CG. Then I'd have to add phase lag. I'd have to add phase lag and move this line up to get it to become marginally stable. Again, that shows you, oops, it's unstable right now. Okay, so that's our phase and gain margins. So we started to look at the relationship between our phase margin and our damping ratio, right? And now we're going to look at how we would actually get or sketch the time response for a specified phase margin. So if we have a basic system, KGH, H is feedback, if we take the open loop transfer function, then we take the Bode plot from that, we plot the Bode plot, and now from the Bode plot we have determined phase margin for the system. So from the Bode plot we've determined the phase margin. We want to determine the closed loop step response, which is our transient analysis. So how do we do this? You know, just like we used the closed loop root location on the root locus, and we said, okay, it's got a certain damping ratio, certain natural frequency, therefore we can plot the closed loop root, the response. We can do something similar here. We use our second order systems data to determine our phase margin versus damping ratio. Right, so that's this. We use this plot first of all, so we've got a phase margin to damping ratio relationship. Next, we take the second order system standard time responses to sketch that second order response for the system. So we use this because we've got our damping ratio. Now we can use this and we can sketch, if we have a natural frequency given to us, or if we know how to calculate it from the Bode plot, then we can get real time instead of just normalized time. Then we do have to note that if the time response is considered to be unsatisfactory, like in other words, too high an overshoot, it's very slow rise time, the settling time is too long, whatever the characteristic is, then we can redesign our controller using our bode plot. The main way we do that is just, well, the two main ways. One is we can change the gain K, the proportional gain, or we could introduce a compensator which adds new lines effectively to the bode plot, which you would then sort of add to the ones that already exist. So let's look at an example of this now. The damping ratio of 0.48 is desired for the system below. Determine the value of the gain K required to give this response. Right? So the first thing we can do is say, well, what phase margin is going to give me a damping ratio of 0.48? So I could determine what does the phase margin I'm looking for, and that's where this graph comes in. And we see conveniently that, as we said here, we determine that our standard data, from our standard data, that the corresponding, the 0.48, which is what's specified here in the question, is our desired damping ratio, corresponds to 50 degrees phase. So that's the phase margin we're looking for, phase margin of 50 degrees. So this is our procedure. We construct the bode plot for the system with a nominal gain. For instance, K equals 1. That would be what we tend to use most of the time. From that plot, we determine the phase margin and compare it with the specification. Right? So once we plotted our bode plot, we can measure the phase margin, measure the gain margin. And then we need to adjust our bode plot so we actually have a phase margin of 50 degrees. And then for a 50 degree phase margin, we know that that means that we want a corresponding phase angle of minus 130 degrees at the crossover, the gain crossover point. So what we have to do is actually move our gain line up and down by changing the proportional gain of the system so that it passes through 0 dBs at this specified frequency, right? So let's have a look at how we do that. So this is the plot from MATLAB of this particular bode plot. This is the transfer function. So when I put it into MATLAB, this is the magnitude plot on the top, the phase plot on the bottom. So what am I interested in here? I want to know how much do I have to move my gain line to get the gain to be 0 dBs at minus 130. Why minus 130 again? Oh yeah, because minus 130 gives me a phase margin is 50 degrees. And we said a phase margin of 50 degrees gives the damping ratio of 0.48, and that's what the question asked for me to provide. That's like my performance criteria. Okay, so we're looking for this phase margin of 50 degrees. So 180 minus 180 plus 50 is minus 130. So this is the frequency at which minus 130 occurs. So let me now find out what's my gain at that frequency. Well, my gain is a bit difficult to measure here, but we make an attempt. And actually, it's 13 decibels because I prepared that earlier and wrote it on here, right? So it's going to be 13 decibels, which means I need to move my magnitude plot down by 13 decibels. It has to go down by minus 13 decibels. And if it does that, then the crossover point of my gain line will occur at the frequency I need it to occur at to give me a phase margin of 50 degrees. That's what we're trying to achieve. Right, so this is the situation we have. We're looking for a phase margin of 50 degrees, which means that the phase has to be or we're looking at where the phase is minus 130, and that frequency, that's where we need our gain line to cross over. So we're going to shift our gain line down so it does that. And we said that delta K is minus 13 decibels. So the change in gain in decibels is minus 13. What does that correspond to in terms of the change in real gain? You know, the kind of gain we would program or put into our controller. So if the change of gain is delta K decibels, then the new gain is going to be our nominal gain, which we normally leave as 1, plus our delta in decibels. But of course, because this is a logarithmic scale, then we could, in normal ratio terms, then that addition is going to become a multiplier because of log characteristics, log, you know. So our gain is our nominal gain times our delta K in ratio. So we have to find, well, what's delta K in ratio terms? If delta K is minus 13 dBs in this case, that means that in ratio terms we have 20 log delta K. Let's subscript it ratio to distinguish it from the dBs. Subscript that one dB. So of course you have to raise this to the power of 10 and take and divide by 20. So that means delta K R equals minus 13 over 20 raised to the power of 10 to take antilogs. 0.224. So if K nom is 1, that implies K new, the new gain that we have as on our controller, is going to be 0.224. So this gain here, setting that to 0.224, and when we do that, hopefully we'll get that desired step response overshoot, right? Which is a damping ratio of 0.48.